Hello everyone, welcome to our second week recitation. This will be a little guide into the quiz worksheet due this week. The worksheet, we're covering thermodynamic properties, and one of the most important things to start with in most types of chemistry, the central science related to both biology and physics. The key here is balancing our chemical reaction, which is to say, if we have a certain number of nitrogen atoms on one side of our chemical reaction, we need to have the same number of nitrogen atoms represented on the product side of our chemical reaction so that we're not losing any particular excuse me, any particular atom, and then the same needs to be true for every other element. So first things first, we have our chemical reaction of ammonia gas reacting with molecular oxygen gas to form mononitrogen monoxide gas or nitrogen monoxide gas and liquid water. Well, in many cases, if this course was taught in general chemistry, or if this topic was taught in general chemistry, a lot of times it's not necessary to write out your work when balancing a chemical reaction. If you can do this stuff in your head, by all means, that's awesome. For step A of part 1, you don't need to show any work, but here's essentially how to do this. We have our chemical reaction, and what we need to see is how many of each atom we have on both sides of our chemical reaction. Well, the only three types of atoms or elements we have are nitrogen, hydrogen, and oxygen. And if we just look right now, what we see is if we have one of each chemical, on the reactant side, we have ammonia, which has one single nitrogen and 3 hydrogen atoms, and molecular oxygen, which counts as 2 atoms of oxygen. On the product side, we have a single nitrogen and we have 2 atoms of hydrogen, and between both molecules, we have a total of 2 atoms of oxygen represented. Usually for these types of problems, it's usually best to save things like hydrogen and oxygen for last if you have something else that's not balanced. Or in particular, try to save the thing that shows up in multiple places on one side of a chemical reaction for last. For example, oxygen shows up in 2 places on the product side. So if multiple things were not balanced, we would try to save oxygen for last because it shows up, because it would be difficult trying to balance multiple things at the same time. But as we look at it right now, the only thing that's not balanced is the number of hydrogen atoms represented. So if we keep going, let's say we put in what are called stoichiometric coefficients, stoichiometry, stoichio or stoichiometric coefficients. These are multipliers to a chemical formula that essentially say we have this number of that molecule, or if it's an ionic compound, that number of this compound. It multiplies the number of atoms represented by one particular chemical formula. So let's say we want to balance the number of hydrogen. Well, on the reactant side, we have NH3. On the product side, we have H2O. 3 hydrogen atoms, 2 hydrogen atoms. The least common multiple would be trying to get to 6 atoms of hydrogen. So we can put a coefficient of 2 in front of NH3, and we can put a coefficient of 3 in front of the molecule H2O, so that we have 2 times 3 hydrogen atoms for a total of 6, and 3 times 2 hydrogen atoms for a total of 6 atoms of hydrogen. However, we weren't just affecting the number of hydrogen atoms, because the formula for NH3 also includes nitrogen. This changes our represented number of nitrogen to 2 times 1, or 2 atoms of nitrogen. And we have on the product side, 3 times 1 oxygen is 3, plus the single oxygen from NO, giving us 4 total oxygen atoms represented. Since we just balanced hydrogen And we're going to try to save oxygen for last because it shows up in multiple places. Let's balance the number of nitrogen now since we just changed that one. Well, that's simple enough. We have 2 nitrogen atoms represented on the reactant side. We have a molecule that contains 1 single nitrogen atom on the product side. So let's have 2 of that molecule. 2 times 1 nitrogen gives us 2 atoms of nitrogen. 2 times 1 oxygen gives us 2, plus the 3 oxygen atoms from 3 molecules of water gives us a total of 5 atoms of oxygen. Well, that 4 right there, the slash between the 4 might be a little bit hard to see, but we're crossing those numbers out. Now we've sort of reached a little bit of a difficulty. The problem is nitrogen and hydrogen are now both balanced as far as the number of atoms of each that are represented, but now our issue is on the product side, we have a total of 5 atoms of oxygen. On the reactant side, the only molecule that has oxygen is O2, and we can't multiply some whole number by 2 atoms of oxygen to get 5. So what we're going to need is to have an even number of oxygen on the right side. Well, we can start by affecting the multiplier in front of H2O, since currently we have an odd number of oxygen just from H2O. So instead of having 3 in front of H2O, let's just multiply that by 2 to get the even number. 6 molecules of H2O. That gives us 6 times 2 hydrogen atoms, or for a total of 12. The goal was to have an even number of oxygen, so we already got that if we left a 2 here and a 6 here. But since we changed the number of hydrogen, let's just balance everything else. We have a total of 12 atoms of hydrogen on the right side, so we can change our coefficient in front of ammonia to 4, so that we have 4 times 3 atoms of hydrogen. Bring that up to 12 on the reactant side. Because that affected the number of nitrogen, we have 4 times 1 nitrogen on the reactant side, which means we should change our coefficient in front of NO to 4 as well. Bringing that number to 4 times 1, or a total number of 4 nitrogen atoms of nitrogen. Now, nitrogen and hydrogen are balanced still. We just went through all the backtracking. Now let's count the number of oxygen. 4 molecules of NO have 4 atoms of oxygen. 6 molecules of H2O have 6 atoms of oxygen. Adding those numbers together, we have 10 total atoms of oxygen. The total on the product side is even, which means we can easily now add a coefficient in front of O2 on the reactant side to balance that. So let's just put a coefficient of 5 in front of the molecule O2. 5 molecules of molecular oxygen count as 5 times 2, or 10 total atoms of oxygen. Doing a little bit of cleanup now, what we see is balancing our chemical equation to have 4 molecules of ammonia, 5 molecules of molecular oxygen reacting together to form 4 molecules of nitrogen monoxide and 6 molecules of water gives us a balanced number of each type of elements. We have 4 nitrogen atoms represented on the reactant side and the product side. On both sides, we have 12 atoms of hydrogen represented, and we have 10 atoms of oxygen represented. So we're done. Just as an aside, for balancing chemical reactions, what you want is the least number ratio comparing all these chemical species. It would be balanced if we instead say had 8 molecules of NH3 plus 10 molecules of O2, yielding 8 molecules of NO plus 12 molecules of H2O. But if you see a situation where you can divide all the coefficients by some number, for example, if it was 8, 10, 8, 12, we could divide all of them by the number 2. That would still get us to the least common the least common factor. So if you have all of your numbers and you can't divide them all by some similar number, then you know you're done. 4 molecules of ammonia reacting with 5 molecules of O2, yielding 4 molecules of NO plus 6 molecules of H2O. Now we have our balanced chemical equation. That's going to be important for solving step B, which is the enthalpy of reaction. That's formally going to be either delta H, or sometimes you might see it written as delta H subscript Rxn. Rxn, that's just a shorthand in chemistry for saying reaction. These are still the same thing though. The proper formula is we need the sum of the enthalpies on the product side minus the sum of the enthalpies on the reactant side. So, using our balanced chemical equation, we'll need 4 times the enthalpy of formation of NO plus 6 times the enthalpy of formation of H2O. Put that all in parentheses, and then we'll subtract that by the reactant sum, which is going to be, if one of our reactants is ammonia and its coefficient is 4, we need 4 times its enthalpy of formation. And then if we have any more reactants, in this case O2, our balanced chemical equation says we have 5 molecules of O2 for every 1 time this chemical reaction occurs. So 5 times the enthalpy of formation for O2. Replacing all these enthalpy of formation symbols to their values from our chart, what we see is we're going to get the total quantity of 4 times 90.29 kilojoules per mole plus 6 times negative 285.5 kilojoules per mole. Whatever all that equals, we'll subtract it by the total sum of 4 times negative 45.9 kilojoules per mole plus 5 times 0 kilojoules per mole. Solving those numbers, we get on the product sum, everything adds up to negative 1,353.64 kilojoules per mole, and we'll subtract that by the reactant sum, which comes up to negative 183.6 kilojoules per mole. Subtracting by a negative just gives us the addition of a positive. Therefore, lastly, for part 1, step B, the final answer is going to come out to be an enthalpy of reaction being negative 1,170.04 kilojoules per mole. These values will be either positive or negative. Unlike in week 1 where positive or negative was used to say some cardinal direction, up, down, left, right, that's only true for vectors going through space. The positive and negative side when it comes to things that involve energy or things that involve the unit joule or kilojoule, that just talks about the direction of whether it's going into a reaction or leaving a chemical reaction. For example, saying that the enthalpy of reaction is negative means that we have released that amount of energy as heat. Think of that as heat as a product of this chemical reaction. If the enthalpy of reaction was some positive value, then that means that that's the amount of heat energy that was absorbed to start the reaction. So if we had a positive total enthalpy, we can think of that number as a reactant in our chemical equation to help these two react together. But when it comes to energy, energy is a scalar, not a vector. because that positive or negative sign deals with the direction of of entering or leaving a chemical system. It does not talk about going up, down, left, right, diagonally. So you will see a positive or negative sign in your answer, but that does not mean that it is a vector. Energy is, or things with energy are still scalars, because that's not a direction in space that the energy is leaving or entering. Now that's all said and good. Let's look at one next part that might be a little bit of challenge, which is phase diagram and calorimetry. What we have here is just some following parameters that are true for just water. And phase diagrams, essentially, at some pressure, there are going to be temperatures where water is either in the solid phase, liquid phase, or gas phase. And at our particular pressure, the values that we care about are the melting temperature of 0 degrees and the boiling temperature of 100 degrees. What these tell us is our boundaries. If water is currently less than, at a temperature less than 0 degrees Celsius, then it will be in the solid phase. If it's at a temperature between 0 and 100, it will be in the liquid phase. And if it is at a temperature higher than 100 degrees, it will be in the gas phase. Depending on the phase our substance is currently in, we will need to use the appropriate specific heat capacity in units of joules all over grams degrees Celsius. And if we have a situation where we need to cross a boundary from either into the solid then liquid phase, or into the liquid then gas phase, or backwards, we'll need to use the appropriate specific heat capacity for our latency. Latency just means we are adding heat energy or taking away heat energy from our system without changing the temperature of our system. Since temperature is not changing, kinetic energy is not changing. But during latency, if we're going from the solid phase to the liquid phase, essentially we are adding heat energy to the solid to increase their potential energy to the point that now all those atoms are collectively in the liquid phase. If we took away energy from a liquid and the temperature did not change, we're decreasing its potential energy until it is in the solid phase. And then once temperature starts changing, that change in heat energy is correlated to a change in kinetic energy. Heat of fusion is just for going between solid and liquid, and heat of vaporization is going between liquid and gas. If we look at our first problem, we're asked, determine the heat energy necessary to convert 2 grams of water from a temperature initially at 50 degrees Celsius to a final temperature of 150 degrees Celsius. Well, if we look at our temperatures for melting point and boiling point, what we see is we're going to initially be between 0 and 100. So we're going to initially be in the liquid phase, but when we end at 150, we'll be above the boiling point, which means we're going to be ending in the gas phase. Because those are 2 separate phases, we're going to need to break up our total equation for solving for the heat over multiple different equations. The first one is, let's look at the change in the energy it takes to raise our 2 gram sample of water starting at 50 degrees up until its boiling point, because that will be the range of temperature that it is still a liquid. Well, that formula is going to be its mass of 2 grams times the liquid specific heat capacity of 4.184 joules per gram degree Celsius times our change in temperature. We're initially at 50 degrees Celsius. The highest we can raise liquid water at this pressure is 100 degrees Celsius. So we'll times it by the quantity of 100 minus 50. Taking all this into account, that gives us a total energy added of 418.4 joules to raise water from 50 degrees to 100 degrees. If we were going from 100 to 50, then that would end up being negative 418.4. But we're actually adding heat, that's why it's positive. Next thing, we've risen liquid water to as hot as it's going to get. So now we have to go through the vaporization latency. The heat of vaporization, Q vape, the amount of energy we added is going to be the total mass of our sample times the specific heat capacity of our latency period of vaporization. You're given two values, one in kilojoules per mole, one in joules per gram. Since we're working in grams and joules, let's use the one that's joules per gram. So taking 2 grams times 2,265 joules per gram gives us a total amount of 4,530 joules of heat added to our system. Then lastly, for the remaining temperature range, we're currently at 100 degrees, and we just moved all of our liquid water to the gas phase. Now we can reach the final temperature of 150 degrees by taking the mass of 2 grams times the specific heat capacity for a gas of water, 2.03 joules per gram degree Celsius, times the temperature range of 150 degrees Celsius minus 100 degrees Celsius, equals 203 joules of heat energy added to raise our sample to the final temperature. Some areas where students in past semesters have gotten errors is they've tried to do the entire temperature range 150 minus 50 degrees, which that's not valid because we can only use temperature ranges for specific phases. So we can't use 150 minus 50 degrees because we're going to be in 2 different phases, liquid and gas. The highest we can raise it is to 100, and then we'll take the remaining temperature difference for the last phase. Let's see, other past errors might have been some students understood that splitting up the temperature range between 150 and 100 degrees, but some have made the error of using the entire temperature range between melting point and boiling point, for example, using 100 degrees minus 0 degrees, when in reality, we would only use 0 if we're starting at 0 degrees. Since we're starting at 50 degrees, that's why we have 50 degrees in our QL, or heat of the liquid phase. To explain these different symbols, QL is my way of saying heat during the liquid phase, QVAP, heating during the vaporization latency phase, and QG, heat added during the gas phase. Nice thing is, we've calculated the amount of energy needed to be added to our system to raise 2 grams of water from 50 degrees to 150 degrees. This took us 3 different steps, so our final answer for step A is going to be adding up all those steps together. So the total heat energy added, or the final answer for part 2 subpart A, is going to be 5,151.4 joules. Be sure to show your work in part 1 and part 2, though you don't need to show your work for balancing a chemical reaction if you don't need to. But let's go into the last subpart, which is B. Here we are asked, convert the heat energy needed, or what's the heat energy needed to convert 1.5 grams of ice to starting at a temperature of negative 20 degrees Celsius to a temperature of 40 degrees Celsius. Since we're raising the temperature, we should end up with a positive value of heat added. If we were actually lowering the temperature, then our final answer would be negative. What we see here is that we have a temperature that's starting below the melting point, And then we have a final temperature that's above the boiling point. So we're actually going from the solid phase into the liquid phase. So once again, we're going to need to break up our total heat energy into multiple calculations. Since we're starting out in the solid phase, Q sub S will equal 1.5 grams multiplied by 2.09 joules per gram degree Celsius, the specific heat capacity while in the solid phase, times the temperature range. We're starting at negative 20 degrees Celsius. The highest we can get it to is 0 degrees Celsius. So 0 minus the negative 20, or 0 plus 20, ends up giving us 62.7 joules of energy to raise our solid sample up to 0 degrees. Now we're going to add potential energy to our system by adding heat energy, raising the potential energy from the solid phase to the liquid phase. The heat of fusion added, the heat added for fusion is going to be 1.5 grams, the total mass, times 333 joules per gram, giving us a total heat added to go from solid to liquid phase, 499.5 joules. And then lastly, we'll get to our temperature range for the liquid phase. Do not put 100 minus 0 since we're not ending at 100. Instead, we're going to take for the liquid phase 1.5 grams times the specific heat capacity of liquid water, 4.184 joules per gram degree Celsius, times the temperature range we're going from. We're starting now at 0 degrees Celsius. That's where our liquid phase begins. And we're trying to get to a final temperature of 40 degrees. We'll still be liquid by that point. So 40 minus 100, multiplying the rest of our equation, we'll get 251.04 joules. And lastly, to get our last answer, just add up all those values. So you have the total energy being the solid phase heat added plus the heat of fusion added plus the heat added during the liquid phase. And that's going to all come out to be 813.24 joules. If for a situation where your temperature ranges do not go into a separate phase, then you would just need one calculation. And if you're, say, going from solid to gas or gas to solid, you're going to need multiple calculations, a total of 5 for the solid portion, fusion, the liquid portion, vaporization, and then the gas phase if we're going from solid to gas, or the exact opposite if we're going from gas to solid. For your exam is actually, while the quiz is going to cover material just this week, your exam is going to cover material from the past week. So your exam is going to be, I believe it's 12 questions. It's usually these exams I try to keep into 15 questions or less. Most of them are going to be knowledge-based questions. Basically, choose one of the multiple choice options given to you. There are going to be, for this upcoming exam, 3 questions that involve math. If you're asked to calculate an answer, you'll be told what the final units should be, just so that you know how big or how small your final answer should be. For example, if it was meters versus millimeters, you'll be told what the unit of your final calculated answer should be, but do not write the unit on your exam because you'll be typing in a number, whether -9 or +9, just put -9 or 9. If the answer was 9 newtons, just write 9. If the answer was -9 newtons, then write -9 numerically. But don't write the unit Newton. That way the system will still know that you typed in the answer correctly. But most of your questions for your exam, they're going to be multiple choice. By all means, have your PowerPoints, your slideshows, your videos out. Totally wonderful. For your quiz, though, this is your quiz for this week, just on week 2 material. And, well, Send in your questions. If needed, we can definitely have another presentation on Friday. If not, then by all means complete your quiz, hand that in, and then work on your exam anytime this week because, again, it will just cover material from last week. And since it's just 12 questions and it will be timed for 3 hours, technically you have 15 minutes per question, but you certainly won't need 15 minutes for most or perhaps any of them. In any case, well, great work last week and keep it up. Peace.